A warm welcome to all of you. I, Akash Sharma, on behalf of MIDAS IT, welcome you all to this webinar on Pile Raft Foundation Analysis using MIDAS GTS NX. So today in this webinar, we'll be following this general workflow. First of all, introduction to Pile Raft Foundation. What is the need? What are the favorable and unfavorable condition? And what is the design approach? Then we'll talk about the numerical analysis, the need, the preliminary and the complete analysis using the software. What are the issues in numerical modeling? The case study where we'll be completing a full model in GTS NX, and finally the result interpretation to conclude with. First of all, about pile raft foundation which make use of raft and piles to reduce differential settlement leading to considerable economy are referred to as pile enhanced raft or pile raft foundations. Now, why the need for pile raft foundation? The first is to reduce the maximum settlement, control the differential settlement, economical design, and whenever there is a lateral loads coming onto the foundation, one need to go for the pile raft foundation. Now, what are the favorable conditions for pile raft? Now, according to Poulos, the following soil profiles are favorable for pile raft foundation, where the soil profile consists of relatively stiff clays, or the soil profiles consisting of relative dense sand. Now, the unfavorable condition for pile raft is situation where one shouldn't go for pile raft foundation are soil profiles containing soft clays near the surface or which has loose sands near the surface, and the soil profiles which contain soft compressible layers at shallow depths, soil profiles which are likely to undergo consolidation due to external loads, and soil profiles which are likely to undergo swelling movements due to external causes are the unfavorable conditions as in for pile raft foundations. Now let us talk about the design approach for the pile raft foundation. It is a two-stage design process. First of all, an approximate preliminary stage is done. It is just to assess the feasibility of the pile raft foundation for the project and estimation of the required number of piles to design for satisfying the design requirements. Then we go for the complete analysis procedure. Now it is obtained it helps us to obtain the detailed design information like what is the final spacing of the piles, what is the pile diameter, and what is the pile location or what arrangement of piles we are going to consider. So this is the two-step process. Now, what is the need for numerical analysis? Why one should go for numerical analysis? The answer to the question is the fact is that whenever there is a pile raft foundation, there are different types of interaction. First, there is pile soil interaction, which is a kind of soil structure interaction, pile pile interaction, raft soil interaction, and pile raft interaction. Now, what happens is that the analysis which can consider all this kind of interaction will give us a more accurate results, and avoiding any one kind of interaction leads to approximation and hence inaccurate results. So that is why one required to go for the numerical analysis whenever we deal with the pile raft foundation. Now let us talk about the preliminary analysis. Now in preliminary analysis, one need to check the feasibility of pile raft and at least predict with the minimum number of piles meeting the design requirements. For example, you can see in the figure that we, we created a model, and one we checked with raft only and the other with pile raft, and you can see that the maximum displacement per unit length is 1 upon 335, or you can even check what is the differential settlement coming in the model with the pile and without the pile, and thus you can see that whether the pile raft is a requirement for your particular project or not, and then move ahead with the complete analysis. Now complete analysis is basically it is obtained for the detailed design information. First of all, spacing of the piles, it is a hit and trial approach initially, then with the based on the previous results one can adjust the arrangement of the piles to get more effective results with the piles. Pile diameter parametric study, you can change the pile diameter and you can see the influence on the reduction in settlement. And the pile location and arrangement of pile, once again hit and trial initially, and then you can use the previous results to justify your next analysis case. So this is how one proceed for the complete analysis of a pile raft foundation. So moving on to the next part is the issues in numerical modeling. Now when we have a building, there are a lot of columns, and for proper stress transfer you need to have node at that particular location. Also after that, if you change some loading in the model, the reaction will change, and once again selecting that load and applying that load on that particular node is a tedious process. Now just to summarize, first is node at column location. For example, whenever you are creating a soil model and you want to apply a column load at a particular location, you should have a node at that particular location. And first thing, and the second thing is you should know that coordinate also, or the node number also. So node at that column location, the solution to this problem is import of the building mxt file from midas gen to midas gtsnx. What you can do is that you can create the building in midas gen, or it's a structural software, structural analysis and design solution provided by midas. So it can be used for buildings and general structures. So you create a model in the gen, you run the analysis, and also what you can do, you can export that file, that mxt file, which is directly which can be imported to midas gtsnx. Okay, now you have the exact column location, and then you can create the soil model around it. Okay, so the first issue is solved. Now the second issue is application of load. Now what happens is that many times when you create a building, now and then you make some changes in it, so the reaction changes. So each and every time going and selecting node and then applying the reaction from the columns is a very cumbersome job. So what midas gts provides you with the option is table input. What you can do is that first you export the load table, which will give you the format in which to input the values. Then what you can do, you can change the value and directly import the excel file and can apply the load. So it will save a lot of time of yours and help in accurate determination of, or accurate applying application of loads on that particular node, so making your job easy. So today in this webinar we'll be focusing on this feature, that how one can import the load from the excel sheet and how to import the building file from gen to midas gtsnx. So moving on, so now we'll move on to today's case study. So in today's case study, we have a building analyzed in midas gen to, which will give us the maximum reaction at the column location. And for this loading, we will generate two analysis case. One will be a raft 1.5 meter thick, and the other will be a raft 1.5 meter thick with 9 piles of 0.8 meter dia. So now I'll just move on to the program so that I can show you the model which we are going to work with. So first of all, about midas gen. So this is the interface of midas gen. Now first of all, as we are discussing the issues, so let us check the node numbers. Okay, now you can see that the column node numbers at the support are 246, 205, 207. Now what we want is that this node when should be the node number when it is when we create the model in the gtsnx, so that when you apply the load, it directly when you import the load from the excel sheet, it will be directly taken. Okay, so for this we have to export the mxt file. Before that, we'll just run the analysis and go to the pre-processing mode. I'll just hide the nodes. Okay, now we'll check for the maximum reaction. So reaction and force, so we'll take the most critical one. So envelope structural for maximum, fz, and say apply. Okay, even if you want to take the values in excel format, you can just take these values. So I'm just taking RC, let's say maximum, just say OK. So this is the maximum reaction coming on the columns, and you can see that which node number 178, 180, 204, 206. So these are the column nodes, and these are the maximum reaction for which we want to check, or we want to perform the settlement analysis in our model. Okay. So next what we'll do is that we'll export. We'll go to file, we'll say export, and there you can find the option mxt file for FEA-GTS. Just give it a name and say save. So the mxt file has been exported. Now what I will do is that I'll move on to GTS NX. So this is the interface of GTS NX. As you can see that everything is tabbed in the workflow. First you have the geometry, all the geometric commands, then mesh, then the type of analysis you want to perform, then generate the analysis case, and finally the result. Okay, now let us start. First we will import the mxt file, which is our building. Say open. So you can see that the building is imported. I will just show you the exact, since it is coming as a line model, because in gen we define it as a line model. The building has been imported, but now right now this building, the importance of this building is that it will help us generate nodes at that particular location where the column is there. Now here it is only 9 columns, but when you have n number of columns, you want to make sure that where you get the nodes, you get the nodes at the column location. So what we'll do is that we'll now create the soil model around it. First of all, let us delete the supports. So you can see this is model. So in the model workstree window, it's very important to understand that whatever you create till mesh goes over here. Then after mesh, like boundary condition and the load set comes in here, even the analysis case, and finally you have the results window. So just go to analysis, go to boundary condition. I'm deleting this mesh set, boundary set, I'm sorry. Now once again I'm moving to model. Okay, now what we need to do is that we need to, I'm just hiding this mesh set, default mesh set. Okay, you can hide unhide from here. Now what we need to do is that we need to create a continuum model, that is a solid model. Okay, so let us create. First of all, just understand the workflow. Whenever you start, first of all think of a 2D simulation of your 3D model, then extrude that into a 3D model. Okay, and then you can move on to the meshing and boundary part. Okay, so first of all we need to create the rectangle, which will be basically the raft. Initially I will create the rectangle for raft. So location being 0 comma 0, enter 9 comma 9. Okay, now 9 comma 9 is method as relative, so in relative to the previous point, which is 0 comma 0, so not much difference when it comes with origin. Just say okay. But now if you see, the rectangle is created on this side, right? The work plane is the xz plane. So first we need to change the work plane. So I'm just saying Control Z, that is undo. Then on the left hand side, go to work plane, click on XY. Okay, now go to rectangle. Now select 0 comma 0, enter 9 comma 9. Fine, now the rectangle is created properly, and now if you activate the mesh, you can see the raft. Similarly, we'll create another rectangle, which will be basically for our soil model. So click on rectangle. So initial coordinates being -4 comma -4, say press enter. What is the next location? So I'm keeping it relative only, and I'm saying 17 comma 17. Press enter. Okay, so the outer rectangle is for our soil model, and the inner rectangle is for the raft. Now what we need to do is we need to create a solid out of it. So this is the 2D command window finishes over here. Then you go to extrude, say click on extrude. So it says select the target object. Now we want to select this rectangle, right? But if you see, if I click, it is not at all selecting. So the reason being, the cursor will select only those identities which the selection filter says. So I'm just changing it to basic wire. Now you can select it. Select the direction. So you can directly use the datum axis. So the it will be Z axis. So what is the length? Let's say 4 meter. Preview, so it's going up, you need to reverse the direction, say reverse it, going down, say apply. Now what happens is that you have created the first layer. Now let's suppose if you have two layers of soil, similarly now select the target object. What I will do, I will just select the bottommost point, bottommost face of the soil. So select the direction, let it be the vertical only, length say 8 meters, preview, going down, fine, okay, right? So now we have created two solids for the soil mass. Now let us create the solid for raft. You can see we have created two solids. Similarly for raft, we'll be doing the same. We'll go to extrude, select the target object. Once again, I'm changing it to wire. I'm selecting the inner, select the direction, will be vertical only, say 1.5, reverse direction, say preview it just to make sure, and say okay, fine. Now once you complete your solid geometry, now these are the only solids which we are going to create. The next solid which we'll be creating is piles. So that will be modeled as a line element. Okay. So before, once you complete, you make a habit of doing auto connect. So just click on auto connect, method, say boolean, select all, and say okay. Doing this, what it does is that it basically performs the boolean operation and it cuts out the raft solid out of the main topsoil solid. Fine. Next we need to generate the piles. So go to line. Now there are two types of line. One is 2D, other is 3D. 2D is basically the line will be created only in the work plane, but for our case, the pile will be going down, that is below the work plane. So I'm using 3D line. So input the location. I'm just inputting the coordinates 0.5, 0.5. Since the raft is 1.5 meter thick, I will insert till uh, minus 0.75, say enter. Now relative 0, 0 and vertical depth being minus 7 meters or 7 meters, say enter. So the first pile is create. Now for rest of the piles you can use the translate command. Just go to transform, say translate. So select the target object, so this line, select the direction, you can use the datum one. So let us make a copy, distance being 4 meters and the number of times being 2. See, now you can just preview it, say apply. Once again select this 3, select the direction, same 4 and 2, preview it and say okay. So with this we have completed our geometric modeling basically. The next step which we need to do is we have to define the material properties. Okay, so whatever you have created, you can check in the workstream window, geometry. So we have created 11 curves, which includes 2 rectangles and the 9 piles and 3 solids. Fine. Now go to mesh, go to material. So I'll just delete it, delete this material. This material property has been imported. So I'll just show you how to define one property and the rest I will import. Say create isotropic. Now what is the model type you want to work with? Let's say more column. Okay, give it a name, let's say soil. So what is the general property? Say what is E value, what is nu value, what is the gamma value, the nonlinear parameter, what is the C value, and what is the phi value. So these are the inputs you have to give, and let's say I'm just saying okay, fine. So I'm just closing it. So after defining this, you need to define what kind of element you are going to assign it. For example, soil is a 3D, or if you are modeling it is a 2D, you have to define the program that we are going to define it to a 2D element. So when you mesh it, then at that time the property will be shown. For example, I'm defining the property as 2D. Okay, just to show that what is the importance of defining property, and I'm giving it a name soil, and I'm selecting the material over here as soil. Okay, now I want to assign the material properties. Now assigning of material properties will be done when you are going to mesh it. Okay, so these are solid elements. When I say 3D mesh, you can see that there is no property coming, so I cannot use that function to mesh. I cannot use that property to mesh. While if I say 2D, now I can use that property, but I cannot mesh the solid because a 2D mesh, right? So that is the importance. So what kind of material you are going to assign it becomes very important. Okay, so I'll just undo the generation of the two material property. I'll go to property and I will import it from other file. Fine. So once you have defined, if the material properties you have defined, you can directly use it in your later projects. Say okay. Fine. Now let us see what material properties we have. We have sand, we have clay, concrete raft for concrete, concrete structure for the piles, pile to soil interface and pile to raft interface in the material properties. And the properties which we have, like for example column, topsoil, bottom soil, we have 3D elements. Raft is also defined as 3D, then pile defined as beam element, and then we have the interface properties. So two types of interface, pile to raft and pile to soil. As I already described, its importance to consider the interaction between pile raft and pile soil. Fine. Now next step is meshing. So meshing is the time when you assign the material property to the geometric model. So go to mesh, go to 3D mesh. Okay, now select the object. I'm selecting this solid, give it a size. I'm giving it a size of 0.5. Hybrid measure. So what is the property? So topsoil, bottom soil. So topsoil for us, initially it is soil. I will later change the material to raft in the construction stage analysis. Let us give it a name, topsoil raft. Now this is very important, naming it, because then only we'll understand that which measures belong to which property. So I'm just saying apply. So it has been meshed. Fine. Similarly, select the other solids, topsoil, give it a name, topsoil main for main soil, say apply. So it is at the time of meshing, as I already told you, that you assign the properties. Okay. Now after meshing, and then the next step will be the boundary condition and the loading. But here, first of all, we need to mesh the model, assign the properties. So we have two types of elements over here. One is 3D, that is for the solids, and we have the 1D, which is basically for the pile elements. Since I have given it to small size, it is taking a bit of time. So this is our topsoil. Now I'm selecting the bottom one. I'm giving it a size of 1. Select the property as bottom soil. Name it bottom soil and just say OK. Now after meshing this, we will mesh the piles and then define the pile interface, and then we have to define pile to raft interface, which I will show you how to define. That is to consider the raft pile interaction, and then we will complete the meshing part. Now in between, if you have any queries, you can write in the question tab box. So once I will complete with the demonstration part, I will reply to your queries directly. So you can write the questions in the question tab box. Okay, now we have created, as you can see, 3 mesh sets which you can find in the workspace window. topsoil raft, topsoil main, and bottom soil. Now all the mesh sets right now are having the soil properties. Okay, now I'll just uncheck this. So it's very important to understand the where you can hide and unhide things so that you can activate only those things which are required at the time of meshing. Now I will mesh the piles, say 1D. Select the objects. You can just say select all. So 9 piles has been selected. We're giving it a size of 1 pile. Give it a name as pile and just say apply. Fine. Now having created it, you can see in the property window that how exactly the pile looks with the pile beam option. Fine. Now next we need to generate the interface. So just go to element, go to pile tip. In this pile, first of all select element. So we have activated only the pile, right? So you can just say select all and just say apply. Fine. Now pile tip. So pile tip is basically the bottommost point of the pile. So you can select like individually, or what you can do, you can just go to front view and just select the bottommost point from one edge. So the 9 tip point has been selected. So this is pile tip. So just say OK. Fine. Now, as you know that all the pile that we have a portion of pile which is inserted in the pile. I will just right click in on it, and transparency I will make it transparent. Okay. So this portion of the pile is also having right now the pile to soil interface. So we have to change it. So what we'll do is that we'll go to element parameters. Okay, so where you want to change the property to 1D, so select the objects. So you can just select those part which is inside the raft. That is why I have make it transparent. Okay, so it has been selected. Now the property is changing. For this portion it will be pile to raft. Just say okay. Fine. Now I will just make once again the transparency to opaque, and I will hide it. Okay, so now we have meshed the models. So what we did till now is that we created a rectangle, two rectangles. We generated the solid model out of it. We used line 3D to define our piles. We used the translate command to arrange the piles, the number of piles, and create the number of piles. Then we define the material and property, and then we mesh the solids, then the piles. Then we created the interface for first pile to soil, and then we changed for the particular portion which is inserted in the raft with pile to raft interface. Okay. Next step, we have to move on to the boundary conditions. So go to static slope analysis. In the boundary you have constraint. So you have three options: basic, advanced, and auto. So first of all we'll go to advanced. Say select all RZ, because we'll restrain the piles in the RZ direction, and please name it as pile constraint and just say OK. So the first one has been generated. I'm activating all the mesh set. I'm removing the default mesh set. Then what you can do, you can just go to constraint. Now I will give constraint to the whole model. Go to auto, give it a name, let's say GS standing for ground support, and just say OK. The program will automatically generate the boundary condition. Right. Now the most important part, now we need to import the load. Okay, the self weight is generated by the program since we imported the file from the gen, so it takes the self weight. Now what we need to do is that we need to import the load at the column location. Okay, so first, to have the format, what you need to do at the first time, you have to define it. Then you can export the load table. Okay, the second time what you can do, you can just go to table, say table import, select the Excel file with particular format and just say open. So let me open the Excel file first, so that I can show you at what values or what format basically we are following. Okay, so this is the format. If you remember, these are the node location for the columns and these are the maximum reaction which we are getting. Okay, so what I will do is that I will import this value. So I'll just give me a second. What I will do is that I'll just remove the boundary conditions from the view. Now what I will do, go to table in the load, table import, select that Excel sheet and just say open. So you can see that automatically at this location the file the nodal load or the reaction from the column has been removed. So next time if there is any change in the value, what you can do, you can just change the value in the Excel sheet and directly import. So you need not create a model or you need not go manually define. For example, here right now we have 9 columns. Original model files you can have 100 of columns. So at that time this feature will become very efficient. Okay, now next, boundary condition. What, till you know the raft is having the ground material property. So what I will do is that I will define a boundary condition. We'll go to boundaries, say change property, construction stage. I'll select this mesh shed and I will give it a property of raft. Okay, and I will just say okay. So when I will activate this boundary condition, what will happen is that the material property will change from ground to concrete or raft which we have defined for it. Okay, now let us go for construction stage definition. So stage set, click, I will just give it a name, let's say pile raft, say add. First, define construction stage. Now, initially the first stage always should be the initialization of stress, where you initialize the stresses in the soil only due to the self weight but without any displacement. As you know, in practical field condition there is no displacement because of the self weight. So topsoil main, topsoil raft, bottom soil, these are our initial soil. You can just say activate, so you can see that what all is activated. So ground support condition, if you check this, you can see that the ground support condition and the self weight will clear the displacement. Clear displacement is basically you are saying the program that not to consider any displacement because of this particular load in the model. Save it, then new. Now in the second step, what we'll do is that we'll activate the soil. This is topsoil raft, right? This, but we'll activate the boundary condition too. So what is happening is that now that particular mesh set is having concrete properties, and we'll activate the piles and the pile constraint too. So second stage we have activated the pile and pile raft. Save it, and the last stage what we'll be doing is that we'll be applying the column load. So just activate. So whatever you want to activate you can activate, whatever you want to remove you can just deactivate in that particular stage. So just save it, close it. So we have defined one, so I'll just make a copy of it. I'll just change the name to, let's say, raft, say modify. So raft, define construction stage. So first stage is okay, and in the second stage what we'll do is that we'll remove the piles because we just want to consider the raft. Okay, so that we can compare the results. So this is a kind of preliminary analysis as I was discussing in the presentation. Just save it. The final stage remains the same, the column gets activated. Close it. Now we have completed the loading part, and then we have defined the construction stage. Final, we go to analysis, go to general, solution type, select it as construction stage. So we have selected the construction stage set as pile raft. In the analysis control data, check the initial stage for stress analysis. So this stage will be considered for the initialization of stress in the soil model. So just okay, say apply. So now you can see that whatever is created goes on the left hand side in the analysis tab along with boundary condition and the load. Then you give it a name raft, select the other construction stage. Once again you need to check this option, just say okay. Now you can perform the analysis. So just go to analysis, say perform, say okay, and you can just give it a name and save it. Now till the analysis runs, I have already analyzed a model and I will just like to show you the results. Now when you go to the results, you have to set spiral raft and raft. With each stage you get the displacement. For example, the initial stage we clear the displacement, so no displacement, but you can find the stresses in the model because uh, we initialized it for stress initialization. Now finally we'll move directly to the third stage, which is basically when we activate the load. Okay, so displacement, so tz, so this is how it is going to displace. Now I would like to show you few of the post processing tools. Okay, now when you move from left to right, here are few of the options. So if you want to see the deform and undeformed shape, you can see that how it is going to deform. Okay, then you go to the advanced option, which are the basically the option which we'll be going to use, like for example probe. For example, you want to probe at the column location what is the value we are getting. So you can see this is the node number, or you can directly input the node number also because we know the node number, or you can directly click on the shaded portion which is basically for the column. Fine, and you can see the displacement which is coming. So you can see that these are the values of displacement in mm. So if you want to check for that particular loading, you can check change the unit system from here. Fine, so this is the displacement coming. Okay, now if you go to the raft one, so you can have a direct comparison. So displacement, I'm saying tz till now. If you see, the maximum value is something around 18. Now if I click tz, now the maximum value is something around 37, right? So this is how you can check that what is the displacement was coming with the piles, without the piles. Similarly, differential settlement, if you see, I will just show you I have just taken the values into the presentation so that I can show you what exact values we were getting with it. Okay, so this are the few reactions. So you get displacement, you get the grid forces, you get the beam element forces. So to see it, what you need to do, you'll just hide the solid methods. Fine, now you have the piles. Go to axial force. What you can do is that I'll just make it undeformed. Fine, and I will close the probe window. Go to results, say axial force. So what is the axial force coming in the pile? So you can see the axial force diagram, the shear force in y, shear force in z, bending moment in the y direction for the piles, bending moment for the z direction. Okay, now the one question which comes into mind is that why we model it as a line element. We could have modeled it as a solid element because it's a 3D software. Now the thing is what kind of results we are interested in. For example, now I can give this maximum bending moment diagram to the structural engineer so that he can design the pile accordingly for the reinforcement. Similarly, you get beam element stresses, you also get the solid stresses, xx direction, yy direction, and zz direction. You get the principal stresses. Okay, so these are all the results which you get. Okay, few of the post processing tools which I would like to show you. Let's say tz. Now these are the tools. Probe, multi-step iso is basically if you want the results, uh, if you want to extract the results, just go to extract. So pile raft, you are interested in tz, so you can just select. For example, it for us it's not very much important because we are interested in the third step. Select any numbers of node and say table. So this will be generated in a format which can be exported to Excel, or you can create the graph directly. Okay, the third option is multi-step ISO. So this basically, for example, TZ, so it shows you a visual pictorial representation of the surface which are having equal displacement, so that you can get an idea of which area to reinforce accordingly. Fine, even if you want to cut your model in, for example, when we are dealing with let's say tunnels, it becomes very important. But if you cut, you can see that what is the displacement contours in the model. Okay, so these are few of the options. First option was probe, important. Extract, when you want it in the format of Excel with each stages. Multi-step ISO pictorial representations of the surface having equal values of parameters which you are interested in, for example displacement tx, ty, or tz. Clipping plane if you want to cut the model. And then you have the ISO value surface. ISO value surface is very similar to the multi-step ISO surface, but it is basically a pictorial representation. What I will do is I will just uncheck the clipping plane, and then I will show you the ISO surface. So it's basically when the value of displacement, you can see that when it's moving, then it is showing you those area which are having displacement greater than it or smaller than it. So it is once again a kind of representation for you. Also with MIDAS GTS NX, for example, you want to export a image. So I'll just select a particular image, let's say TZ, say OK. So what it will do is that it will export that image. I'll just select, let's say, for the third stage where we can see some values, TZ, say OK. So the model will automatically be imported to the 3D PDF where you can directly probe it and directly save it. So instead of going for print screen, what you can do, you can directly export it into the PDF. Okay. Now let us move on to the presentation part. Now let us interpret the results which we get. Now if you see that what are the displacement in vertical displacement at the column location, so you can see that there is a huge difference in the settlement with raft and without raft for that particular loading. So the maximum was something around 39.17 mm with raft, and which reduced to 18.47 with pile raft. Okay, so this is a basic comparison of the 9 columns. So if you see with raft only, the maximum settlement beneath a column was 39.30, minimum settlement was 36.05, so a differential settlement of 3.25 mm was there. Now with pile raft, the maximum settlement decreases, so the minimum also decreases, and also the differential settlement decreases. So that is the, as I already in the initial slides of the presentation, I already discussed that it helps in reducing the maximum settlement as well as the differential settlement, so which can also be seen through the results. Now with this, I would like to conclude today's session. So to summarize, today we learnt about the design approach of pile raft using the numerical analysis, consideration of the superstructure model from MIDAS Gen to MIDAS GTS NX, import of load with the help of Excel file, which will be very important while dealing with practical issues, effectiveness of pile raft in reducing the differential settlement. Okay. So with this, I would thank all of you to join this webinar. Now, if you have any queries, you can write to us at techsupport@midasit.com. The next webinar will be on soil structure interaction for sword excavation using 3D finite element analysis. That is on June 2nd, Indian Standard Time, 4 p.m. and for UAE, 2:30 p.m. So thank you very much. Hope to see you in the next session.